So our next speaker is going to be David Stanford. Okay, he is going to be talking to us about open source hardware design. Give him a hand, please.
I like the cats so much that Denise had it earlier that I went in and updated my slides to grab something from her website. So I hope she doesn't mind. My workplace, like apparently every other presenter's workplace, wanted me to disclaim some things since I was coming here. None of the stuff that I'm telling you they necessarily agree with. They also don't want you to take any of this as investment advice. So I'm going to talk about open source hardware design. We're going to start off, like, what is hardware design for? What sorts of things are you going to do if you're doing hardware design? Well, you can get CPUs, cell phone radios, graphics processors, video game emulators, robots, self-driving cars, all that sort of stuff comes out of hardware design. And I've been doing this for about 20 years, and in doing that have done radar jammers, test equipment for missiles, laser gyroscope controls, network protocol engines, trading accelerators, and this is all using field programmable gate arrays, which I'm going to talk a little bit more about later. So that's great, but what could somebody here use it for? I'm doing it for my job. You guys probably don't want to do my job. You were doing your own jobs. But if you're going to want to do this in your home, doing hardware design could give you exposure to more layers of abstraction. We were talking about what an operating system is before. If you're doing hardware design, you can forget what an operating system is because you're doing real full stack development. You're going from all the way down to the ones and zeros. If you have a dev board you bought somewhere, you can use new features of it from that. If you want to emulate some old Atari system, hardware design can help you with that. If you have some sort of setup at home where you want to glue a lot of different functions together, hardware design can help. Or if you're using some small microcontroller to run your aquarium at home or run a home security system, and you need to offload some sort of fish detection system, a hardware accelerator can help you with that. That's all with FPGAs, and they can make hardware design like software design, making any security that you want to do or updates possible to do later. So maybe you're a little bit interested. What is that actually going to look like? Is that like truth tables, these ones and zeros that I remember taking a look at in school? That's a little bit about what's going on, but that's not how it goes anymore. It's not really Boolean algebra so much either. This might be something that you had seen in school as well, where you have pluses and dots and XOR signs that are kind of hard to understand with this plus sign that's circled up. Mostly if you're doing hardware design, you're not going to be doing gate layout design either. However, if you're doing this at home on your own, this is a sort of setup that might be a good place to start. But what I usually do when I'm at work is System Verilog. It's a language that looks like every other programming language that anybody is using, with a set of inputs and outputs, and I say that the outputs are going to be the sum of the inputs. But you don't need to use a language that's unfamiliar to you. You don't need to necessarily learn a new language. Python, for example, can do the same thing that System Verilog is doing. So you've got a language. How do you end up actually turning that into a chip? FPGAs is what I talked about earlier, and that's what I use all the time when I'm doing this. FPGA stands for Field Programmable Gate Array. The gate array portion means that it's a large collection of logical building blocks. It's going to be a bunch of gates, ands and ors, nots that we talked about, multipliers, sums, memories, and interfaces to the outside of the world to be able to talk to everything else. The field programmable part means that the silicon is reconfigurable after leaving the factory. A lot of times if you were doing computer chip design for someone like Intel, you're designing a CPU, that first chip that's going to come off the line costs $1 million or $10 million, and then the second one is like $10 or 10 cents. FPGAs end up being a little bit more expensive, but there are dev boards that you can buy and take home that are going to be between like $50 and $100. So how do you end up actually programming that language to the point where you can get it into the chip? You start off by compiling your code, and you're going to want to simulate it ahead of time. We don't have an operating system. We don't have a bunch of cats that are going to be able to tell us what's happening here. So simulation is very important for hardware design because you don't have a lot of visibility once it's in the chip. After you compile the code, Synthesis is going to take the code and turn it into a lower level sort of layout of what those basic components are of the target device is going to be. Then placing tools are going to take those components and actually put them around on the chip. They're going to be placed on the different locations based on what those components need to be. And then routing tools are going to go in and they're going to route the logic in between those different chips, making sure that all of your constraints for timing or pin layout end up getting met. So I started off talking about open source. Why would anyone actually care about that? So I use closed source tools at work. I work on really big, complicated chips. But the open source tool chain is a lot smaller, it's easier to license, and there's a lot lower barriers to entry. The tool chain I use at work is 40 gigabytes to download. It'll take 5 minutes to get a Blinky Light compiled and out. The open source tool chain is on the order of a couple megabytes, and you can get from Verilog codes to Blinky Light in closer to 5 seconds. The open source hardware components are also the ones that the entire community are helping make better. We found a bug this week on vendor libraries where they tried to do bit positioning and their code is wrong. It's been wrong for 5 years. And it's vendor code and we can tell them it's wrong and maybe they'll eventually fix it. But one of the benefits of using open source tools is there will be GitHub projects out there so you can say, you know what, you have misplaced this comma here, you misspelled your undefined, can you please fix this? Alright, so you're easily convinced, and I've convinced you already. How do you get in to actually do this? The right way to start is to get a cheap development board with something called a Lattice ICE40 chip. There's a lot of development boards out there right now. This is a very active area where folks are really excited about this. More than just me. Folks also in hardware design are really excited about this, so there's a lot of development boards that are out there. And then start off with something called iStudio. It's a GUI interface that gets you all of the other tools that you need and has board support packages, so you just can download the iStudio, plug your chip into your USB port, and throw some gates on there and get to Blinky Light so fast. If that's simple for you, you're like, you know what, I'm going to get to Blinky Light. I already have done that before in a college class. I want to do something more complicated than that. What the FPGA is a great tutorial that's out there. It's out there for multiple boards, but the Icebreaker board here goes through more than just Blinky Lights. It goes through registers and summing numbers together and dealing with some of the more complex things that you could get into in design. So you're still in, and you want to get even deeper. So what do you do next? The next up would be trying tools in the language that you already know. Python, Scala, C and C++, Java all have active hardware communities out there. You can write stuff that goes directly into hardware from those languages. Or you could track down RISC-V CPU implementation and download it onto the board that you've had. RISC-V is an open ISA instruction set architecture that is really popular with folks that are doing open hardware. Or you can read the deep dive on Hackaday on that ICE40 FPGA that you got on that development board so you can know more about the low-level details of all the components on that chip. So that's it. Everyone's excited, ready to go home and get started. Here's some links to track that down, and the slides will be up on my Twitter if you want to track any of them down later. Thanks.